All right, let's go ahead and start talking about weak acid and strong base titrations. So now that we have a weak acid present, we're going to have to introduce our acid dissociation constant like we did for our previous unit on acids and bases. So the first thing we're going to do is calculate the pH before we add any of our titrant. So this will be just like a problem that we've solved previously. We'll start out with our acetic acid, and then we'll look at the dissociation. So we'll end up with hydronium, and then also acetate as our products. We'll fill up our ice chart with the initial concentration, 0.100 molar. Don't worry about water because it's a pure liquid. And then for hydronium and acetate, there's 0 initial concentration. Our change will be minus X plus X because Q is 0, so the reaction must proceed to the right. And we'll end up with 0.100 minus X, then X over here. So we know that Ka for acetic acid is 1.8 times 10 to the negative fifth. Plugging in, we'll have X squared divided by 0.100 minus X. Just like we've done previously, what we'll do is, because this number right here, 0.100, is on the order of magnitude 10 to the negative first, and then Ka is 10 to the negative fifth, since there are more than 3 orders of magnitude separating these two values, we can ignore the X. So from here, we'll multiply the 0.1 over, take the square root, and we'll find X is equal to 0.0013 molar. And then plugging that in for the pH, we'll have the pH is initially 2.9 for this solution. So now we want to look at the titration. What happens before we reach the equivalence point? So here we're going to calculate the pH after we've added 20 milliliters of sodium hydroxide. So we're going to start by writing out this equation here where we're looking at our acetic acid reacting with our base, the sodium hydroxide. We leave the sodium out because it's going to be a spectator ion. But now, for whenever we're looking at an acid being neutralized by a base or vice versa, we have to convert these concentrations to moles because we aren't interested in the concentrations canceling each other out. We're interested in the actual moles. So remember that molarity is equal to moles over volume. So rearranging that, we'll get volume is equal to moles divided by molarity. Sorry, I don't know why I just did that. We're going to be solving for the moles. So we will have moles is equal to molarity times volume. So we'll plug in our initial concentration. We'll have 0.00400. So that will be 0.00400 moles of acetic acid, 0.00200 moles of hydroxide. We have 0 initial acetate, and then we'll subtract off the smaller number here. So this hydroxide will neutralize 0.00200 moles of our acetic acid. That means that we'll end up forming 0.00200 moles of acetate. So whenever we go through, we're left with 0.00200 moles of acetic acid, 0.00200 moles of acetate. Before we can plug this into an ice chart for the dissociation constant of an acid, we need to convert these mole amounts to concentrations. So the way that we're going to do that is we'll divide by the total volume, which is 0.0600 liters, which gives us a concentration of 0.0333 molar. So now we're ready to set up our ice chart for the dissociation of our weak acid. So we'll do the exact same process that we did before we added any hydroxide. Alright, so now we have our reaction written. So we can plug in our initial amounts, our change. So we start out with initial concentration of 0.0333 molar. 0 for the hydronium, 0.0333 molar for the acetate, minus X plus X. We know this reaction is going to the right because we have no initial hydronium, so Q is equal to 0. So then we'll have 0.0333 minus X. We'll have X 0.0333 plus X. And then we can use Ka again. So remember that Ka is equal to 1.8 times 10 to the negative fifth. We'll have X squared over 0.0333 minus X. So we'll have X squared, and then that will also be plus 0.0333 X. Let's rewrite this numerator like this. We'll have X times 0.0333 plus X. So in this case, again, look at how Ka is 1.8 times 10 to the negative fifth, and these values are 10 to the negative second, so we're getting close to being two orders of magnitude separated, but here we're only 3. So what we can do is we can ignore both of these x's, and now we have 0.033x divided by 0.033. Well, the 0.033's both cancel out, so x is equal to Ka, which means here that our pH is equal to 4.7, and at this half of the equivalence point, so see how we've added half of the moles of OH minus of what we initially started, pH is equal to the pKa at half of the equivalence point. So now we want to go ahead and study this at the equivalence point, and something happens at the equivalence point. So let's go ahead and write out our reaction. So we have acetic acid being neutralized by hydroxide, going on to form water and acetate. So you have the choice of either picking up where you left off, or what I like to do is start from the beginning every time. So start off with 0.00400 moles of acetic acid. At the equivalence point, we can calculate this out because we know that the moles is equal to molarity times volume. We've added 0.00400 moles. And then we'll assume we have 0 initial acetate, so then this will be minus 0.00400 moles. And what we'll see is both of our reactants completely cancel out, and we're left only with acetate. So this is 0, this is 0. This is 0.00400 moles. We need to go ahead and convert that to a concentration, so we're currently at a total volume of 80 milliliters. So that's 0.0800 liters. So our concentration here is 0.0500 molar. We can't write an expression using Ka because we don't have any initial concentration of acid. What we can do is we can write an expression for the dissociation of a base, with a Kb. So we'll have our conjugate base up there, CH3COO minus plus H2O, goes on to form acetic acid plus hydroxide. So here, we'll go ahead and set up our ice chart. Our initial concentration is 0.0500 molar. And if you're using an acid or a base constant, then you are going to have your ice chart in terms of molarity. If you're looking at neutralization, you're going to have it in terms of moles. 0 initial acetic acid, 0 initial hydroxide. We have minus X plus X plus X. 0.0500 minus X plus X plus X. Okay, so now, again, this is for a Kb reaction. So we need to find Kb for ammonia, or for the acetic acid. So Kb is going to be equal to Kw divided by Ka. So you can plug in your values and you end up getting a Kb value of 5.6 times 10 to the negative 10th. And then we can plug in our expression. So we have x squared over 0.0500 minus x. So in this case, if we compare Kb, which is 10 to the negative 10th power, and then this value here is to the negative second, that is definitely more than 3 orders of magnitude. So we can ignore that x. And now from here, we can go through and solve for x. So x equals 5.3 times 10 to the negative 6th molar. But now this is the concentration of hydroxide, so you can find your pOH to be 5.3, and then your pH to be 8.7. This is just like what we've predicted before in class, that if you mix a weak acid and a strong base, that your equivalence point, that the pH should be basic. And that's what we found. The pH is 8.7. So as we move past the equivalence point, some of the things that you'll notice, so we go about the same way. We set up our initial ice chart, and we go ahead and start with the starting amount of acetic acid, but now we've added past the equivalence point of hydroxide. So now you can solve that out, and you're left with some moles of hydroxide and then moles of acetate. So now we have an initial starting concentration of hydroxide. So we still use that Kb reaction. But now whenever we write this out, so we have 0.040 molar here, minus x, and then we have the 0.0200 molar there. We plug that in for Kb, and what we see is that, again, Kb is to the order of the negative 10th, and both of these numbers here, the initial concentrations are only to the negative second, so that's more than 3 orders of magnitude difference, so that x doesn't matter. So we don't actually have to go through to solve for x at all, because we know the initial concentration of hydroxide, and it's not going to be changed at all by this plus x term here. So what we can do is we can calculate the pOH from this value right here, the initial concentration of hydroxide, and then subtract it off from 14, and you can find the pH to be 12.3. So many times with weak acid and strong base titrations, once you get past the equivalence point, you don't actually have to set up this secondary ice chart. You can just calculate the pOH and the pH from whatever leftover hydroxide or hydronium you have. So what I like you to do now is try to logic your way through the weak base titrated with a strong acid example, and then in just a second here I'll walk you through each of those steps. Alright, so for the weak base with a strong acid titration, what we're going to do, same thing. So here we know what Kb is for ammonia. It's 1.8 times 10 to the negative 5th. We'll set up our ice chart. So we'll have ammonia acting as a base, forming the ammonium ion and the hydroxides. This is a Kb reaction, so a base reaction. So we can go through just like we normally did. We have 1.8 times 10 to the negative 5th is equal to x squared over 0.1 minus x. Again, since Kb is to the negative 5th and our initial concentration is to the negative 1st, what we can do here is we can ignore that x right there because it won't change our denominator appreciably, and then we can solve for x. From there, you're able to find the pOH from this x value, since that's our concentration of hydroxide, and then plugging in, since we know that pOH plus pH equals 14, we can find the pH. Before the equivalence point, once we've started our titration, so now we're adding acid. So we have our ammonia plus our H+. We have to go through and find the amount in moles first. So we start out with 0.00400 moles of ammonia, 0.00200 moles of the acid. Subtract off the small amount, and we see again that we have the exact same starting concentrations of ammonia and the ammonium ion. So just like we did with our previous example of the weak acid and the strong base titration, now we're plugging in for Kb instead of Ka, and we get Kb is equal to 1.8 times 10 to the negative 5th. we have our values. Initial concentration is 0.0333. Since those are to the negative second, we can ignore this x value in both cases. So we can find the pOH, and we should find that the pOH is equal to pKb for this specific example. And then we can subtract off and find the pH. Now at the equivalence point, the same thing happens as with the previous titration. So we have equal mole amounts of ammonia and hydronium, and that means that at this point in time, only the conjugate acid is present. And so once we find that concentration, which is 0.0500 molar, we need to go through and find Ka for ammonia, or for the ammonium ion. So we're able to find Ka because we know that Ka times Kb is equal to Kw. So we find that Ka for this particular acid is 5.6 times 10 to the negative 10th. You're able to set up an acid dissociation constant reaction. So we have 0.0500 molar minus x, 0 plus x, 0 plus x. We have our ice chart. So now, whenever we solve for x, what we'll find is, because we can cancel this out, that x goes away. So you multiply by 0.05, take the square root, you can find the pH directly because x is equal to the hydronium concentration. And then the same thing will happen once we've passed the equivalence point. So here you'll start out with ammonia, add your hydronium, end up with the ammonium conjugate acid. So here the only thing that's left over would be hydronium. We've consumed all of our ammonia, and you also have an ammonium concentration there, which that should be molar. You can plug into your ice chart. But again, look, so Ka is 5.6 times 10 to the negative 10th. Both of our initial concentrations are to the negative second, so we can ignore those x's. So this 0.0200, we can find our pH from that initial concentration, and we find this to be 1.7. So many of the questions we will ask will be at the equivalence point, and what we'll see there is if you have a base and a weak base and you're titrating with a strong acid, you may be given a Kb value. So that means you're going to have to go through and find Ka and then write a reaction like we did here. So I hope this helps, and we'll talk about polyprotic acids and multiple equivalence points later.